Hello folks, and welcome to the second video in the linear relations unit. In the last video, I kind of touched on what a linear relation was, and in this one we'll kind of take a bit of a deeper dive into understanding what they are and what they look like. So let's get right into it. So here we go. Here's just jump off with an example. So we have a scuba diver going underwater, and the weight that the water exerts on the diver in terms of pressure is given by these two things right here. So first thing we have is what is known as a table of values. And I touched on a table of values in the first video, but here's another example of a table of values. Okay, we have the depth of the diver. So as they go underwater, deeper and deeper and deeper, right? And we have the water pressure that is being exerted on the diver in kilopascals. Fun, fun. Now over here, we have something a little bit different. We have what is called a graph. And these two things are actually displaying the same information. If we look at our table of values and we look at the numbers that are associated with it, and we look at the way that these columns are labeled, we have the depth of the diver given in meters. And if we come over to my graph here, I see that we also have the depth of the diver given in meters. And then we have the approximate water pressure given in kilopascals. And again, over here, we have the approximate water pressure given in kilopascals, right? We have the same information on both the table of values and the graph. And this line, you'll notice, actually has the same information as these numbers, because on my x-axis, we see the numbers that represent these numbers in my left side of my table, and on my y-axis, right, we usually call the horizontal axis the x-axis and the vertical axis the y-axis. But on my y-axis, we see that we have the numbers that represent the pressure. So if I find those numbers, so 0 meters and 0 pressure, so I'm at the point 0, 0. Then 5 meters and 50 kilopascals of pressure, so 5 is right here between 0 and 10, and 50 is right here between 0 and 100. And I notice I get another point that falls in this red line. And if I look at for 10 and 100, again, I see the same thing. In 15 and 150, again, I see the same thing. And finally, 20 and 200, I see the same thing. I get 4 or 5 points that actually fall on this red line here. So we should notice a pattern. So graphically, what we see is that the pattern these points make actually gives us a line. So if we're thinking about the name linear relation, linear, we see that the first 4 letters actually are just the word line, right? Because that's what happens when we look at these things on a graph. What we see is that they actually end up giving me a line. Now, if we look at our table of values, how do we know this thing's going to give me a line? We see that it has what we call a constant rate of change. So if I'm looking at my depth of my diver, every time we jump forward 5 meters, my pressure goes up by 50 kilopascals. So from 0 to 5 is 5, and 0 to 50 is 50. Then from 5 to 10 is another 5 meters, and from 50 to 100 is another 50 kilopascals. And then from 10 to 15 is another 5. And then from 100 to 150 is another 50. And we notice that we have this, again, constant rate of change, where as these numbers change by some constant amount, so in this case, they're changing by 5, these numbers over here also change by a constant amount, in this case, 50. So there's really 2 ways to recognize these linear relations, or 3 if we're thinking about the equation. But this is what happens. When we give them as a table of values, we should see this constant rate of change. And when we're given them as a graph, we should see that these things have a line. So let's take a look at a couple of examples of picking these things out. But before we do, let's just quickly look at what the actual written definition of linear relation is. So when the graph of the relation is a straight line, we have a linear relation. And again, should be relatively straightforward because the first 4 letters are the word line. In a linear relation, a constant change in one quantity produces a constant change in the related quantities. So if we look back at our previous example, a constant change in the diver's depth produces a constant change in the water's pressure. And notice how it said one of the quantities and then the related quantity, because in the previous video, I talked about independent versus dependent variables. And this is that idea where we are going to approximate the water's pressure based on the diver's depth, because usually that's how we think about it. However deep the diver is, because that's what they have control over, will tell us how much pressure the water is exerting. So the pressure of the water depends on the diver's depth. And usually we order our variables in a way that makes it so that this first column is what we call the independent variable. Independent, meaning that the diver has control about what his depth is. And then the second column is the dependent variable. And again, this is the one that depends on how deep we are. So let's take a look at an example. Do we see some linear relations here? So if I'm looking through these graphs and I'm trying to decide, are they linear, are they not linear? All I really want to know is there a pattern that looks like a line? So I'm looking at graph A, I see these points, right? And I see this line that attaches them. I see that they form a line, so that's linear. Yep, sure is. Graph B, same thing. I'm seeing these points, and when I attach these points, I get a line. Again, the line means that it's linear, right? There's no guessing. If I see a line, it's linear. Now, graph C, you might look at and say, well, that's not a line, it's just the points. And you would be right, there is no line here. But if there was a line, if we kind of imagined that I drew in an imaginary line here, what shape would that line take? Well, based on those points, the shape of that line is linear. So, yep, this is a linear relation. So even though the points aren't attached like they were in graphs A and B, it still forms a line, so it's linear. Now, if I'm looking at graph D, now they're attached again, but in this case, we see that it has this little curve to it. So because it's curved, nope, that is not linear, right? There's no constant rate of change happening there. We see that it grows, like it gets faster and faster and faster. It grows up, so that's not linear. And then in graph E, we're like, okay, well, there's a line, and there's a line, and there's another line. But the idea with these things is the lines should not change. Once they're set, once I have 2 points that kind of indicates my line is going this way, it should go that way forever. So this thing also is not linear. And then from a table of values, same idea, right? We can describe a linear relation, or we can figure out if a relation is linear by looking at its change. So if I'm looking at my x numbers here, we see that they go up by 1, go up by 1, go up by 1, go up by 1. So that's constant. So I should be looking over here and again deciding if this is constant. So 4 to 13 it goes up by 9. 13 to 22 it goes up by another 9. 22 to 31 it goes up by another 9, and then 31 to 40 it goes up by another 9. So there we go. We have this nice little constant rate of change. So does this thing represent a linear relation? Yep, sure does. If its relation, describe it. So when it says to describe it, really what it's looking for, it's asking you to write out the equation. So how does x and y relate to each other? So again, we talked about in the last video how when I'm looking at this rate of change, I'm seeing that we're adding 9, we're adding 9, we're adding 9, we're adding 9. So even though I don't know what the thing that is constant is yet, I do know what is happening. We're adding 9 to this thing. So I can start there. I can say, well, that is the repeated addition. So every time I add another x, I add another group of 9. So it's 9x, because that's what I'm changing by. But then I need to figure out how I'm going to make these numbers actually happen. Because if nothing else, right now, if I threw a 1 in for x, I would get y is 9. But I'm supposed to get y is 4. So what do I have to do to that 9 to make it a 4? I have to minus it by 5. So we have to be able to look at these things and write out an equation based off of that. And again, this number right here, the thing that I am changing by, right, that constant rate of change is going to help me figure out the number that goes with the variable, the number that goes in front of the x. Then we can use these numbers to help me figure out what it has to be at the end. So in this case, we can test. We can say, okay, well, 9 times 1 gives me 9, but then when I minus 5, it gives me the 4 I'm looking for. Perfect. 9 times 2 gives me 18, right? I take this 2, plug it in for x, and I get 18. And then when I minus 5, I get the 13 I'm looking for. Awesome. And then if I checked it for 3 and 4 and 5, what I would find is I get the numbers that I'm looking for. All right, let's take a look at question B now. Is this thing linear? So again, how do we know? Well, we look at the rate of change. It's going down 1. It's going down 1, down 1, and down 1. So when I come over here, well, we go up 3, up 3, up 3, and then finally up 3. So again, nice. What we see is that we have a relationship that takes these x's and turns them into y's. So again, that's linear because our rate of change is constant. It's doing the same thing on the left-hand side and the same thing on the right-hand side. Now, this is a nice example because, look, we have negative, but negative's okay as long as it stays negative. It has to do the same thing every single time. So how do I then write out this relationship? Well, I can say y equals, and we might instinctively say, well, it's supposed to be 3x. Just like in the last question, that 9 told me that the 9 goes in front of the x. But the problem is, when we were looking at this question, we were going forwards. We were going 1, 2, 3, 4, 5, and so on and so on. So that was okay. That one worked out. But when I come over here, it doesn't actually work that way because we're not counting forwards. We're actually counting backwards. So if I went the other direction, if I went up from my table of values, so instead of going down from 9 to 5, if I thought about going from 5 to 9, I see that I get plus 1, plus 1, plus 1, and then minus 3, minus 3, minus 3. So we can use that minus 3 in front of our x this time in order to put that number where it's supposed to be. And then from there, we need to figure out what we need to add on to this thing in order to give me the values I'm looking for. So we can just pick one. So if I use the 9 or I use the 5, it shouldn't really matter. So let's use the 5. So if I plug the 5 in for x, I get negative 3 times 5. And that gives me negative 15, right? And to that, I have to add something. I have to add something to that in order to give me the answer 20. Well, the number that I need to add is 35. And again, if I checked any other pair of numbers here, the 9 and the 8 or the 8 and the 11, I should see that this works. All right, so we've looked at how we take a table of values and write out an equation, but we should also be able to go the other direction. We should be able to take an equation and write out a table of values. And it's a little bit easier to do it in this direction because it's pretty intuitive. All this is really telling you to do is take these numbers and put them into your equation where you see an x. So I take this 1, I put it in my equation, I get 2 times 1, and I get 2. I take this 2, I put it in my equation, I get 2 times 2, and I get 4. Same thing with the 3, and then same thing with the 4. Then I don't need to worry about doing too many of these. So let's do another one. So again, take this 1, put it in your equation. This time it's not 2 times x, it's x plus 2. So 1 plus 2 is 3. 2 plus 2 is 4. 3 plus 2 is 5. And 4 plus 2 is 6. Notice in this first one, my rate of change, again, is 1 for my x's, and for my y's, it goes up 2, up 2, up 2, and that 2 is going to come back to the 2 that's in front of the x. But over here, we go up 1, up 1, up 1, and again, that 1 helps me figure out what number is supposed to be in front of the x. All right, let's do one more here. This time we have negative. So again, if I plug a 2 in, I get negative 4. If I plug a 4 in, I get negative 8 and negative 12 and negative 16. And notice the rate of change here, instead of going up, we are going down. And that's what that negative in front of the 2 tells me is supposed to happen. All right, so let's actually take a look at an example of one of these things and see if we can't kind of go from beginning to end, okay? So here we go. We have DVD rentals, which these notes might be a little old at this point. I don't even know if you can rent DVDs anymore, but here we are. So we are told that the cost to rent a DVD is given in the following table. For one DVD, it's $3.50. For 2, it's $7. For 3, it's $10.50, and so on and so on. So the first thing it asks us to do is it asks us to graph the data. So in order to graph the data, we need to know what my two axes are going to be. So I have a y-axis and an x-axis, so I need to know where they're supposed to go. So again, when I'm thinking about this data, usually if I'm renting something or I'm paying for something, the number of things, so in this case, the number of DVDs is my independent variable. So that's going to go on my x-axis. So down here, I have number of DVDs, right? And then on my y-axis is the other variable, and that is simply just the cost, right? C-O-S-T, perfect. So we're being told that for one DVD, it's $3.50. So if I'm jumping by 1, 2, 3, 4, 5, and 2, 3, 4, 5. That makes sense to jump by ones on my x-axis. So 1, 2, 3, 4, 5. And then my y-axis, I can probably jump by 2. So 2, 4, 6, 8, 10, 12, because I need to go all the way up to 17.5, 14, 16, and finally 18. And now we graph. So 1 and $3.50, 2 and $7, 3 and $10.50, 4 and 14. Brain stopped working there for a second. 4 and 14, and then finally 5 and 17.50. So 5 and 17.50 is there. All right, so there's my graph. Perfect. Now, part 2 of question A says, does it make sense to join the points? So if we think back a couple examples ago where we had these two different linear relations, one where the points were connected and one where they weren't, when do we do that and when do we not? Well, we call the different types of data continuous versus discrete. And the idea essentially is, can I rent 1.5 DVDs or 2.5 or 2.7 DVDs? And the answer is no, right? It's either 1 or it's 2 or it's 3, but it's nothing in between. So when I use a line to connect these points, what I'm saying is that it's possible to get an answer somewhere between 1 and 2. But in this example, it's not possible to do that. So we actually leave our points unconnected. We don't want to connect them because we don't want to be looking at any values between the numbers 1 and between and 2. So we leave them unconnected. So is this relation linear? So again, the idea is, does it make a line? Graphically, we can see, yeah, that's a line. Or on my table of values, we can see, yeah, it has that constant rate of change, up 350, up 350, up 350. Finally, use the table to describe the pattern in the rental costs. How is the pattern shown in the graph? So again, what does it mean? Well, you could describe what's going on here. It is $3.50 per DVD. Right, like it's not secret that that's what's happening here. It's going up 350, up 350. So that's what it's saying. It's $3.50 per DVD. And then how do we see that in the graph? Well, we can actually see it by looking at the change that happens. How far do we have to move to get from one point to the next point? Well, we have to move over 1. So to go from 1 DVD to 2 DVDs, we move over 1. And then to go from my price of 350 to 7, we go up 3.5. And then again, what happens? We go over 1 and we go up 3.5. Right, so we see this again, 350 per every 1 DVD purchased. All right, so lastly, this is a very common type of question where here's an equation. There's no real connection to what's like a scenario. It's just saying, here's an equation, tell me something about it, right? So work with this equation to actually see what's going on. So let's do that. So we're given an equation, y equals 6 minus 3x. And the first thing we're asked to do is to make ourselves a table of values. Again, x and then y is usually the way that we put these things in. And we're being asked to make our table of values from -3 to 3. And it makes sense in these types of questions that we do want to use negative numbers because they can help us understand the pattern and the relationship that's going on. So there's my -3 to 3. Now, how do I fill in my y? Well, we use this equation provided to figure out what these numbers are supposed to be. So what I'm going to do is I'm going to take this -3 and I'm going to plug it in for x. So we get 6 minus 3 times -3. So 3 times -3 is -9. So this thing turns into 6 minus -9, or 6 plus 9, which is 15. Okay, next one, we get 3 times -2. So this turns into 6 minus -6, which is 6 plus 6, so 12. And then 6 minus -3, or 6 plus 3, which is 9. 3 times 0 is 0, so 6 minus 0, which is 6. And we can see, hopefully, now that there is a pattern happening here. What's happening as I move one space on my x-axis? Well, I have to move 3. So 15 down to 12 is down 3, and then down 3 again, and down 3 again. So 6 minus 3 is 3. 2, so the next one, 3 minus 3 is 0. And then another down 3 gives me -3. All right, part B sends then to graph this thing. So it is useful to make ourselves a linear relation, so make ourselves a table of values when we're trying to graph these things, because now it's simply a matter of throwing these coordinates, these pairs of points on my graph. So let's do that. So again, we're only going up to 3s, so we can jump by 2s on my x-axis. So 3, 6, 1, 2, 3, and 1, 2, 3. So we're only going to plus or minus 3. But on my y-axis, I have to go all the way up to 15, so I got to make sure I can fit that. So I'll probably jump by 2s, 2, 4, 6, 8, 10, 12, 14, 16, and into the negatives as well. So we get 2, 4, 6. We'll go all the way down to -6. We'll have to go down to -3, so I don't have to go too far. So -3 up to 15, -2 up to 12, -1. We're going up to 9, 0 up to 2, 4, 6. 1, we're going up to 3. At 2, we're at 0. And then finally 3, we're at -3 right there. All right, perfect. Now, in this question, it says, do we connect the points? So whenever there's no context to the question, more often than not, the answer is yes, because could I have plugged in 1.5 or 2.6? And the answer is yeah, I could have, right? So these values do exist between these points, and there will be an answer there. So in this case, I would connect the line or connect the points with a line to indicate that I can have answers that lie in between these numbers. So again, we're looking at these patterns. What's happening here? What is this changing by? Well, every time this one went up by 1, this one goes down by 3. So how do we see that here? Well, we see it graphically. Every time we went over one space, we had to go down 3, right? Over 1, down 3, and so on and so on. So the same pattern that was happening here over 1, down 3, we see it on our graph as well. And again, is this thing linear? Yeah, sure is. Graphically, it makes a line. Table of values, we see that constant rate of change. All right, so that is it for this video. Hopefully we kind of pulled away a little bit more about these linear relations, and I will see you all in the next one.